Welcome students, you are welcome to third part of chapter 1 in unit 3 higher order linear differential equations. In the second part of chapter 1, we have learnt about the procedure to determine solution for homogeneous linear differential equations of order n with constant coefficients. To continue with the same chapter, we now move on to find solution of homogeneous linear differential equations of order n with constant coefficients for the case when all the roots of auxiliary equation are real and distinct. To solve a homogeneous linear differential equations of order n with the constant coefficients, one first solves the auxiliary equation to determine roots. Now, based on the nature of roots, we can find general solution for f of dy is equals to 0. Here, f of dy is equals to 0 is the symbolic form of homogeneous linear differential equations of order n with constant coefficients. Let's begin with the case 1. In this case, all the roots of auxiliary equation are real and distinct. So, if m1, m2, so on, mn be the n different roots of the auxiliary equation, f of m is equals to 0, then we have y is equals to e power m1x, y is equals to e power m2x, so on, y is equals to e power mnx are all independent solutions of f of dy is equals to 0. Therefore, the general solution of f of dy is equals to 0 is linear combination of independent solutions of f of dy is equals to 0. Therefore, when all the roots of auxiliary equation are real and distinct, the general solution of f of dy is equals to 0 is y is equals to c1 times e power m1x plus c2 times e power m2x plus so on plus cn times e power mnx. Now let's see some example problems for case 1, that is when all the roots of auxiliary equation are real and distinct. First example, solve d cube y by dx cube plus 6 times d square y by dx square plus 11 times dy by dx plus 6 times y is equals to 0. Now find the solution of the given differential equation in example 1. To do this, first write the given differential equation. Next, write the symbolic form of the given differential equation. For this, we know that d cube is equals to d cube by dx cube, d square is equals to d square by dx square, and the differential operator d is equals to d by dx. Now, replace these terms d cube, d square, d in given differential equation. Thus, we get d cube y plus 6 times d square y plus 11 times dy plus 6 times y is equals to 0. From the left hand side of this equation, we can take out common y. Thus, we get the symbolic form of the given differential equation like this. D cube plus 6 times d square plus 11 times d plus 6 of y is equals to 0. Therefore, we get f of d is equals to d cube plus 6 times d square plus 11 times d plus 6. Here, in f of d, replace d with m. Thus, we get the auxiliary equation of the given differential equation like this. F of m is equals to m cube plus 6 times m square plus 11 times m plus 6 is equals to 0. Now find the roots of the auxiliary equation to get the general solution for given differential equation. Here, the auxiliary equation is an algebraic equation of degree 3. So, it has 3 roots. To find roots, factorize the polynomial in the algebraic equation, that is m cube plus 6 times m square plus 11 times m plus 6 by synthetic division. Here, remember, synthetic division is used to factorize those polynomials whose degree is greater than or equals to 3. Let's see the process for synthetic division. For this, first look into the factors of the constant in the polynomial m cube plus 6 times m square plus 11 times m plus 6 where the highest degree coefficient is 1. It means the m cube coefficient is 1. In this polynomial, the constant value is 6. So take the factors of 6 which are 1, 2, 3 and 6. Now take both the positive and negative values of these factors which are minus 1, minus 2, minus 3, minus 6, 1, 2, 3 and 6. Now by trial and error method using these positive and negative values one can find a root for the auxiliary equation, that is f of m is equals to m cube plus 6 times m square plus 11 times m plus 6 is equals to 0. Now choose m among these numbers minus 1, minus 2, minus 3, minus 6, 1, 2, 3 and 6 and check whether it can be root of the auxiliary equation f of m is equals to m cube plus 6 times m square plus 11 times m plus 6 is equals to 0. It means if we substitute any of these values in f of m, we should get 0. Here I took m is equals to minus 1. Now replace m with minus 1 in f of m. We get f of minus 1 is equals to minus 1 whole cube plus 6 times minus 1 whole square plus 11 times minus 1 plus 6. Simplifying this value, we get 0. Therefore, f of minus 1 is equals to 0. Here remember one point. We can check with the other numbers also to satisfy f of m is equals to 0. If we won't get f of minus 1 is equals to 0, but here we got f of minus 1 is equals to 0. Therefore, minus 1 is the root of the auxiliary equation f of m is equals to 0. Thus, we have m minus of minus 1 is a factor of the polynomial m cube plus 6 times m square plus 11 times m plus 6. Therefore, we have m plus 1 is a factor of the polynomial m cube plus 6 times m square plus 11 times m plus 6. Now follow the synthetic division to divide the polynomial m cube plus 6 times m square plus 11 times m plus 6 by the factor m plus 1 to get the coefficient for this division. To do this, first draw the L shape like this. Inside this, place the coefficients and constant of the polynomial. That is, the first number is 1, which is coefficient of m cube. Next number is 6, which is coefficient of m square. Next number is 11, which is coefficient of m. Next number is 6, which is constant of the polynomial. Outside this, place minus 1, which is taken from the divisor m plus 1, that is m minus of minus 1. Now, the process begins like this. Inside this, place 0 below the first number, that is 1. Initially, add 1 and 0. We get 1. Next step, multiply minus 1 with this 1. We get minus 1. Place this minus 1 below 6 and add 6 and minus 1. We get 5. Next step, again multiply minus 1 with 5. We get minus 5. Place this minus 5 below 11 and add 11 and minus 5. We get 6. Next step, again multiply minus 1 with 6. We get minus 6. Place this minus 6 below 6 and add 6 and minus 6. We get 0. Thus, doing this process, we get 3 new numbers 1, 5 and 6. Now using these 3 numbers, we want to write a new polynomial which is 1 degree less to the dividend polynomial. Here, the dividend polynomial is of degree 3. So, we write a new polynomial which is of degree 2. That is, 1 is for coefficient of m square, 5 is for coefficient of m, and 6 is constant of the polynomial. Therefore, we get the polynomial m square plus 5 times m plus 6, which is the quotient obtained when the polynomial m cube plus 6 times m square plus 11 times m plus 6 is divided by the factor m plus 1. So we get the divisor m plus 1 into the quotient m square plus 5 times m plus 6 is equals to the dividend polynomial m cube plus 6 times m square plus 11 times m plus 6. Thus, by synthetic division, the polynomial m cube plus 6 times m square plus 11 times m plus 6 has factorization m plus 1 into m square plus 5 times m plus 6. Now find the factors for the quadratic polynomial m square plus 5 times m plus 6 using factorization method. For this, take the polynomial m square plus 5 times m plus 6 and split the middle term of the polynomial, that is 5m, using the factors of the constant term 6 in the polynomial. To do this, choose the factors 2 and 3. And when we add 2 and 3, we get the coefficient of m, that is 5. Thus, we get m square plus 5 times m plus 6 is equals to m square plus 2 plus 3 of m plus 6. Simplifying this, we get m square plus 2 times m plus 3 times m plus 6. In this expression, from the first two terms, m square plus 2m, take out common m. And from the last two terms, that is 3m plus 6, take out common 3. We get m into m plus 2 plus 3 into m plus 2. From this expression, we can take out common m plus 2. We get m plus 2 into m plus 3. Therefore, m square plus 5 times m plus 6 is equals to m plus 2 into m plus 3. Thus, the polynomial m square plus 5 times m plus 6 has factorization m plus 2 into m plus 3 by factorization method. Now we have the auxiliary equation f of m is equals to 0. Now substitute the factorization of the polynomial m cube plus 6 times m square plus 11 times m plus 6 in the auxiliary equation f of m is equals to 0. We get m plus 1 into m square plus 5 times m plus 6 is equals to 0. From this, we have m plus 1 is equals to 0 and m square plus 5 times m plus 6 is equals to 0. Now in the equation, m square plus 5 times m plus 6 is equals to 0. Substitute the factorization of the polynomial m square plus 5 times m plus 6. We get m plus 2 into m plus 3 is equals to 0. Thus, we have m plus 1 is equals to 0, m plus 2 is equals to 0, and m plus 3 is equals to 0. From this, we get m values like this. M is equals to minus 1, m is equals to minus 2, m is equals to minus 3. Therefore, m is equals to minus 1, minus 2, minus 3 are the roots of the auxiliary equation, which are clearly real and distinct. Therefore, using these roots, we can write the general solution for the given differential equation, that is y is equals to c1 times e power minus x plus c2 times e power minus 2x plus c3 times e power minus 3x. Thus, the general solution of the given differential equation is y is equals to c1 times e power minus x plus c2 times e power minus 2x plus c3 times e power minus 3x. Let's see one more example for case 1, that is when all the roots of the auxiliary equation are real and distinct. Second example, solve d cube y by dx cube minus d square y by dx square minus 6 times dy by dx is equals to 0. Now find the general solution of the given differential equation in example 2. To do this, first write the given differential equation. Next, write the symbolic form of the given differential equation. For this, we know that d cube is equals to d cube by dx cube, d square is equals to d square by dx square, and the differential operator d is equals to d by dx. Now replace these terms d cube, d square, d in the given differential equation. We get d cube y minus d square y minus 6 times dy is equals to 0. Now, from the left hand side of this equation, we can take out common y. Thus, we get d cube minus d square minus 6 times d of y is equals to 0, which is the symbolic form of the given differential equation. Thus, we get f of d is equals to d cube minus d square minus 6 times d. Now, here in f of d, replace d with m. Thus, we get the auxiliary equation f of m is equals to m cube minus m square minus 6 times m is equals to 0. Therefore, m cube minus m square minus 6 times m is equals to 0 is the auxiliary equation for the given differential equation. Now find the roots of the auxiliary equation f of m is equals to 0. Consider the auxiliary equation m cube minus m square minus 6 times m is equals to 0. Now, from the left hand side of the auxiliary equation, we can take out common m. Thus, we get m into m square minus m minus 6 is equals to 0. Thus, we have m is equals to 0 and m square minus m minus 6 is equals to 0. Now, the equation m square minus m minus 6 is equals to 0 can be written as m plus 2 into m minus 3 is equals to 0, since m plus 2 and m minus 3 are the factors of the polynomial m square minus m minus 6, which can be obtained by the factorization method. Thus, we can write the equation m square minus m minus 6 is equals to 0 as m plus 2 into m minus 3 is equals to 0. Thus, finally, we get m is equals to 0, m plus 2 is equals to 0, and m minus 3 is equals to 0. Now, from these equations, we get the values of m, which are m is equals to 0, m is equals to minus 2, and m is equals to 3. Thus, m is equals to 0, minus 2, 3 are the roots of the auxiliary equation, which are clearly real and distinct. Therefore, using these roots, we can write the general solution for the given differential equation like this. Y is equals to c1 times e power 0x plus c2 times e power minus 2x plus c3 times e power 3x. Therefore, y is equals to c1 times e power 0x plus c2 times e power minus 2x plus c3 times e power 3x is the general solution of the given differential equation. Now, some practice problems are given related to case 1, that is when all the roots of the auxiliary equation are real and distinct. To learners for practice. So learners, try to solve these practice problems. Next, in the coming videos, let's see how to find general solution of homogeneous linear differential equation of order n with constant coefficients for remaining cases, which arises while solving the auxiliary equation. Let's see what we have learned. We learn to find the solutions of homogeneous linear differential equations of order n with constant coefficients when all the roots of auxiliary equation for given differential equation are real and distinct. We will meet in the next video lecture, students. Thank you.